Microphone. How's that? Good. So I'm going to talk about domain-specific languages again. I'm going to talk about something quite simple and easy and shallow about domain-specific languages. So I don't think I'm going to tell you anything you don't already know. I might be telling you something you didn't know that you knew. That was my situation when I did this work. I was giving some lectures on domain-specific languages and trying to work out what they have to do with folds, and I didn't know what I'm now going to show you. So this was new to me. It's joint work with Nick Wu from Oxford. He apologises for not being able to be here. He's just had they've taken delivery of a new baby, and so he's kind of preoccupied with that. So here's a very simple language, an insultingly trivially simple language, just so you get the ideas. And I'm going to show my examples in terms of this very simple language. And at the end, I'll show you briefly the outline of a more realistic DSL. And the paper is expressed in terms of this more realistic DSL. But for the purposes of the presentation, I'll just use this very simplistic one. So it's a language of expressions. Just for variety, it's not literals and addition, it's literals and subtraction. But there's a point to that, that'll come back. So languages have a grammar, syntax, and some semantics. So the grammar here, I've just shown it to you is in facts now, and the semantics very simple, a function that gives some meaning to those expressions. And we know there are two ways of doing this kind of thing as a domain-specific language, as an embedded domain-specific language, I should say. So there's a deep embedding and a shallow embedding. And the deep embedding on the left there, the terms in your language are implemented as constructors of an algebraic data type, and all they do is build terms in this algebraic data type. And the semantics is an interpretation function over these terms. It just evaluates by traversing the structure. And on the right-hand side, there's a shallow embedding. And here you dispense with the syntactic structure altogether, dispense with the algebraic data type. There is no algebraic data type. Instead, you go straight to the semantics. So you implement your DSL directly in terms of the semantics that you're going to provide it. So I'm providing integer semantics for my expressions, so my representation of expressions is just as integers. And then I have literals, I have subtraction. Literals are implemented in terms of integers, subtraction is implemented in terms of integers. And there are dualities between these two. There's a duality about where the work is done, whether it's done in constructing the expressions or interpreting the expressions. You'll see for shallow embedding, the interpretation is trivial. That's gone because there is no final step. There are dualities in extensibility. So for a deep embedding, it's straightforward to add other terms. Sorry, straightforward to add other valuation-like functions, but more complicated to add other terms. And you have the dual kind of extensibility properties of a shallow embedding. So the deep embedding is a very simple thing. It's kind of the natural thing that you might first do, but shallow embeddings are the trendy thing. So many embedded DSLers are in favor of shallow embeddings. They write papers saying we should do shallow embeddings because X, Y, and Z is sometimes called semantics rather than syntax-driven development and so on. So deep embeddings is all about algebraic data types, and there's a big exhibition going on. It's all about trees and technology. If you want to go and find more about trees and technology, then you just need to go to the cool stuff that's going on. Now, that evaluation function, remember that evaluation function. I'm sure you can remember it, you don't need me to show it again. That's why it was such a simple example. It's a fold over the algebraic data type, which is to say, the evaluation of a term is constructed out of the evaluation of the components of that term. You don't need anything more about the components than their evaluation. It's compositional. And it shouldn't take you much thought to convince yourself that that is a necessary property of a semantic function and interpretation if you're going to use it as a shallow embedding, as the semantic domain of a shallow embeddings. Shallow embeddings can only be compositional because you build up the terms as you go, and having built up a term, that's all you've got is the interpretation. And so the next level up, that's all you can use is the interpretation. So compositionality is a required property of shallow embeddings. So the shallow embeddings are necessarily folds over the abstract syntax that is given to you by deep embeddings. This is what I knew, but didn't know that I knew before I wrote this paper. And this makes me very happy because I like folds, and I know lots about folds, and we all. I mean, there's decades of technology and experience, and we can use this in telling us about domain-specific languages. So suddenly I'm more of an expert on domain-specific languages than I ever thought I was. This is great. But then you might wonder, shallow embeddings can only be folds. I can write some things as folds, but it's a bit difficult writing other things as folds. Is this limiting? Is there all sorts of things that I can't write as shallow embeddings because they have to be expressible as folds? Well, this is where what you know about folds comes in to help. Suppose I want to provide a second interpretation of my language. So here I'm interpreting these things as strings with parentheses and so on. Easy to do, trivial to do with a deep embedding. How do I do it with a shallow embedding? I have to pick the semantic domain. I've already picked integers as my semantic domain. But it's not too difficult. I can give still a single interpretation, but now as a pair. A bit clunky. I'm going to show you something better, but it works. So now my semantic domain is pairs consisting of integers and strings, and literals is a pair consisting of an integer and string, and subtraction is done in terms of integer and string pairs. And I knew this. I didn't know that I knew this about shallow embeddings, but I knew that I knew this about folds. Two folds, a pair of folds, working independently like this, is itself a fold. That's the commonly known as the banana split theorem from the algebra programming. Banana because the banana brackets for folds in the 1980s fashion, and split because that's the thing that generates a pair using two different functions. What about dependent interpretations here? So here's a function that produces a string, but in a slightly smarter way. So it does the minimal parenthesization. It only puts parentheses around the sub term if it's on the right-hand side of a subtraction. That's the only place where you need the parentheses. So I need to know whether that term is a subtraction. So it only puts parentheses around subtractions, something like that. Anyway, it's I need to know something about the term other than its parenthesization in order to work out whether to put parentheses around it. That's not obviously a fold, so it's not obviously something I can write as a shallow embedding, because in order to do the printing I need to know about whether it's a subtraction as well. But that's okay, that also fits, because I can do that also as a pair. I can write two interpretations. Now they're not independent ones, they're one depending on another. And more generally I can have two interpretations each depending on another, mutually dependent interpretations. And my knowledge of folds tells me that that's fine too. Two mutually dependent folds are again a fold, so that's still compositional. That still works fine. Here's another way of doing the same problem. You can think of it as a context-sensitive interpretation. You pass in the precedence of the surrounding context, and that tells you whether or not you need to parenthesize in this context. And again, that's not obviously compositional, because the interpretation of a term depends not just on the term, but on the context in which that term is found. How are we going to do that? So this cprint function here, mprint is not a fold over the term, because it depends on a context, and the context varies as you recurse into the term. So the recursive calls are not done using the same function on each of the subterms. But again, it works fine. cprint is not a fold, but flip cprint is a fold. Flip is the thing that takes a function of 2 arguments and makes a function of 2 arguments the other way around. It's a fold over the first argument, evaluating a term, which is evaluating an interpretation of that term, which is a function, a higher order interpretation. It's a function from context, which in this case is just a Boolean, to string. So rather than interpreting your term as a string, you interpret it as a bool to string. That's sometimes called an accumulating fold. And that too is a fold. It's just another kind of fold. And so what we know about folds applies here. More importantly for DSLs, this tells you that context-sensitive interpretations are themselves compositional. They are valid interpretations for shallow embeddings. So there's various things that we can do that might not obviously fit the pattern of folds, but knowing what we know about folds, it all works out. There's this nice quotation from Oleg in some lecture notes he did for a summer school in Oxford that I ran. He said, explicating the context dependency turns a context-sensitive interpretation into a compositional one. That very elegantly says what I want to show here.
It was easier when you said it.
I did tell you it's going to be shallow. So multiple interpretations again. We can interpret terms as pairs, but that's rather clunky. If you want 3 interpretations, it has to be a triple. If you want 10, it has to be a very wide tuple. If you don't know how many you want, you can't really do it as a tuple at all. What can we do about that? With a deep embedding, it's not a problem at all. What about shallow embeddings? Well, I've just shown to you, convinced you, I hope, that all shallow embeddings have something in common. They're all folds. So why don't I just interpret once as what they all have in common, which I can then use, I can then specialize in various different ways to get the various interpretations that I want. Well, what they all have in common is fold-like things, so let's interpret them as fold-like things. What I'm showing you here is the church encoding of this expression data type. Well, Oleg again would tell me that it's not the church encoding, it's the Bone-Maruducci encoding because it's typed. A clever higher order representation, a clever higher order semantic domain in which to make my interpretations. If you haven't seen this before, this will be mysterious, so just bear with me. But there is some type there, expression, which I'm going to use as my domain of interpretation, and literals build one of these things, and add takes 2 of these things and combines them to make one of these things. And you don't really need to know what the thing is. The point is you get some interpretation which you can then specialize to any fold over the term. So here I'm specializing it to do the evaluation by fixing the remaining parts that I've missed out from this recurring pattern. The remaining parts are the arguments that you would give to the fold, the identity function and the subtraction function. So I've done this here in a explicitly passing in the arguments this identity and subtraction. I could do it implicitly passing in the arguments as well. You could do it through a type class. So you could identify a type class of suitable semantic interpretations of expressions, and those things would have to have something to interpret literals and something to interpret subtraction. And integers are a suitable interpretation, and this is how you do it. If you spend a bit more time thinking about embedded domain-specific languages, as for example in Feldspar, so the Chalmers people have been doing this DSL for hardware called Feldspar. Josef Svenningsson and Emil Axelson's paper from TFP in 2012 talked about combining deep and shallow embeddings. So here the idea is that you can think of 2 kinds of language, 2 levels of language. There's a core language and some defined terms, some syntactic sugar on top of that. That's a nice way to design your DSL, because you implement the core once, and that's the thing you have to do the back end for, but then you provide nicer syntax for people writing programs in your DSL. But that also fits this pattern here. The semantic domain in which you do the interpretation is another algebraic data type. It's not the deep embedding of your DSL. In fact, it's a deep embedding of a different language, of your core DSL, if you like. So the semantic domain is kind of somewhere in between. I've heard Leonard Albertson give a talk where he calls these things neritic embeddings. They're not deep, they're not shallow, they're in between. The neritic layer in the ocean is the bit that's on the edge of the continental shelf, so it's between the shallow and the deep. That's Leonard's idea. So I promised you something slightly less trivial than, well, that's why I wanted subtraction, because I can define addition in terms of subtraction. So I can make my core language just have subtraction, and addition is syntactic sugar. So the paper has a more elaborate, perhaps slightly more realistic DSL for scan circuits, parallel prefix circuits. This is based on a paper by Ralph Henzer from 10 years ago, from Master Program Construction in 2004. The circuit on the top right of the slide is a little parallel prefix circuit of size 4. Each of the idea is that values come in the top and they flow down the wires. At each blob, there's some associative operator on the values. At each blob, all the incoming values are added together, combined using this associative operator, and distributed out on each of the outgoing edges of the blob. And so if you work through values A, B, C, D going across the top, you'll see that coming out the bottom you have the prefix sums, A plus B plus C, A plus B plus C plus D. So Ralph's paper talks about a little, he doesn't call it this, but he calls it an algebra of scans, but it's an embedded DSL of scans, built up in terms of these 5 constructors, identity, which is just parallel wires, fans, which copy a value across a bunch of wires, one circuit above another circuit, one circuit beside another circuit, and then a stretching thing which allows the connections to hop over intermediate wires. And those are all you need to build all sorts of scan circuits. And there's a nice algebra of them. They have various algebraic properties about associativity and abiding and so on. There's a deep embedding at the top. There are various different interpretations you might want to make of this language, various different semantic domains you might want. So you might want to find the width or the depth of a circuit, so integer interpretations are one of these terms. You might want to ask whether a circuit is well sized. It only makes sense to put one circuit above another circuit if they have a common width, because the wires are supposed to match up. You might want to apply a circuit. So this apply interprets a circuit as a list of A function for some associative A. So this is the sort of intended semantic domain of these things, but there are other semantic domains too. You might even produce a layout of your circuit, a picture of your circuit, as a list of connections in some sense. And that's how my diagram is drawn. I have an interpretation of this circuit as an SVG, or something from which I generate an SVG file. So that's another interpretation of these circuits. You can do all that on the deep embedding, of course, but these are all compositional interpretations using some of the variations on folds that I've shown you, accumulating folds and mutuomorphisms and so on. So they're all valid shallow embeddings too. So I encourage you to read the paper. I can't go through the details of that. We're running out of time, and Garen's getting a bit jumpy at the front. So I'm going to end there. So my take-home messages: deep embeddings are algebraic data types. Shallow embeddings are folds over those algebraic data types. We know a lot about folds, so that tells us a lot about domain-specific languages. Incidentally, it's perhaps no surprise that if you look at DSLs in the OO context, if you go to Splash and talk about DSLs, they're more often standalone languages. If you come here and talk about DSLs, they're more often embedded DSLs. And I think that's because to do the embedded ones properly, you need algebraic data types and higher order functions. So of course, that's going to be more appealing in a functional setting than in an OO setting. Compositionality is important, and but we can regain compositionality when it wasn't so obvious that we had it. And you can make it all data type generic. That's in the paper. These folds are all really common. They're not just variations on the idea of folds. They really are all folds in a common abstract categorical setting. So channeling Ralph, who's not here, Ralph Finzer, who's not here, he would say they're all adjoint folds. We had a paper at ICFP last year about the zoo of unifying the zoo of structural recursion patterns. So they all fit into that unifying picture, but that's the story for another time. Thank you.
And please, just one question per questioner. No fear of queuing up with a few.
Okay, Josef Svenningsson from Chalmers. Very nice talk. Can you go back to the slide about the generic interpretation? Yes, so this is a very nice trick. We can now compose these shallow interpretations and so forth, and that, I think this is a really nice trick. But what seems to have happened here is that we've so let me go back a little bit. So the duality between deep and shallow embedding is that we can extend them in one direction but not the other. So it's hard to extend the number of constructors for shallow embedding, but not for deep embedding. But here you seem to have fixed having this tuple of functions. You seem to have fixed the number of functions in your shallow embedding. So it seems like we've sort of it's harder to extend them all of a
So
sudden.
you sacrifice some of the extensibility by doing this in some sense.
Right.
Yes.
So what's up with that?
I'm not sure I have a good answer to that. I know Oleg in his lecture notes on the finely tagless approach talks about that.
Yeah, you can make a subclass to extend, but then you can't compose it with the sort of previous thing, at least not immediately.
Yes, I'm not sure. I haven't worked through the details of that, so I'm afraid I don't have a good answer to that. It seems that you now have to use other techniques to get extensibility in the dimension of adding new constructors.
Okay, I'll just ask Oleg then. Thank you.
Yes.
It's always a good algorithm, actually.
You might not understand the answer.
So you're right. I now know something that I knew but didn't know I know. And it's nice to see that one can apply all these tricks we know from folds to think about structuring our domain-specific languages. I think that's my takeaway from your talk. But I was expecting, when you started out this week, say we know lots about folds. One thing we know, for instance, is how to fuse folds. I was expecting you at some point to say, using this analogy to folds, we can make this program 10 times more efficient by doing a fusion here using our well-known technique from folds. And you never said it.
No, that's ICFP 2015, perhaps. So I think you do that in Feldspar, don't you? I think that there's something about getting or maybe Joseph should know, there's the fusion for free in this way. Anyway,
Yes.
I haven't thought about that, but I plan to look further into that.
This is Paulio from Intel Labs. This is all nice, but your example is not complicated enough. What about binders? What about recursion?
Well, I'm not sure what you mean by recursion. They're both recursive languages, and it's a recursive algebraic data type. Binders, I admit, is a different problem.
By recursion, I mean you want to express some kind of recursive relationship in your DSL. When you do deep embedding, you can use some kind of fix. You can tie the knot
Right.
in data type, but when you do a shallow embedding, you cannot, because the knot is tied in host language. It's not in.
Right. That's kind of related to binders as well, isn't it? So yes, I've only shown you very trivial languages. That's all I've explored. I don't know how this works with higher order abstract syntax or something like that. Sorry.
Thanks.
So I apologize for giving a little OO pitch, but the extensibility in terms of data type constructors works wonderfully in Scala if you have mixing composition.
Right.
Last question.
So all of your examples were fold-like, right? You print things or you evaluate things.
Yes.
How does this play out when you just want to do transformations? Like you want to write an optimizer for your expression trees, right? So that's what what compilers do all the time, of course, and so I tend to use deep embeddings all the time. Is it equally easy to use a shallow embedding for that? And what advice do you know about which of these two to choose? You're kind of a bit saying, well, you could use this, you could do this.
So
what would you do?
You can always retrieve the deep embedding from the shallow embedding. The deep embedding is another fold-like thing. So you're not making any commitment by picking the shallow embedding. If you, Oleg's got his hand up, let me put words in his mouth. If you go and read the finely tagless paper, you'll find you can do all sorts of partial evaluation tricks, even on the shallow embedding. So it's surprisingly expressive. I hope that's what you were going to say.
Is that what you were going to say? Thank our speaker again, and now it's time for